Volumes, day one, such a powerhouse lesson. And if you walk right through it with me, I don't think you'll find it too overwhelming. There's lots going on here, but the method actually is very nice. And you've seen part of the method before. So as we have seen in the past, Riemann sums can be used to estimate volumes. The diagram on the right should be familiar. This is a problem we did before. And the idea is to break a large volume up into individual. Well, see, this picture gives cylinders. It doesn't have to be cylinders, although cylinders is very convenient. And if we break it up into little cylinders like this, we can use the integral to sum the volume of each of these cylinders up, and with that, find the volume of the whole shape. So this thing's called a paraboloid. Like it's a parabola, but it's a 3D. It's as if the parabola was spun around the x-axis, sort of like almost like a Dixie cup type shape, but not a cone, but this is bowl type thing. Now to see how this definite integral could be constructed, consider the graph of the solid r at x below. So instead of that one, think about this pink picture down here. And if you can find a function for the area, so the area that they're talking about is this little area of this little shape right there, whatever that is right there. If you can find a function that describes that area as you go along there, I'm not saying that's going to be easy all the time. No. What I'm saying is if you can find a function, then each of those little partitions, that areas, has a width. You say, okay, so instead of it being a little flat, like piece of bologna looking there, but we sort of think of it as a little tiny slice of bread, if you want. And that little tiny slice will have a volume. What will its volume be? Well, it'll be whatever its area times its height is. And the height just happens to be the delta x, the width, the little width of x that you're going to divide this up into. So the volume each time is made up perfectly of area times the delta x. It's perfect. It's perfectly set up for the integral. Now you have to add them all up though. So you need this sigma to add up all the little pieces. Now, when you look at this picture, go back to this picture for a second. See the missing areas up there? You might think, well, it's missing all those pieces. No, it's not. As you let the limit go to infinity, as you do an integral instead of a Riemann sum, all that's taken care of. The answer will approach the proper answer and make those little pieces infinitely small that you're missing because you're making the individual slices individually small. It's beautiful. It's a beautiful setup. So, if we take the limit to n goes to infinity, what we get is this beauty, this beautiful equation for finding volumes. If we can find the cross-sectional area as a function of x, that will get more and more difficult as these lessons go along. But today, pretty straightforward. If we can find that cross-sectional area equation, and by that I'll show you exactly what I mean with a nice simple one in just a second, example 1 at the bottom of the page, then to find the volume, we're going to add up all these little areas times height. See, that's the little area right there, and that is the little height of the little piece of bologna there, the little slice of bread that you're taking out of it. It's going to have some area, and we're going to multiply it by the height, and that height is going to be the little dx in the picture here, this little tiny bit. It's like how thin are the slices, and the thinner you make the slices, the more accurate the volume. So, as we go to infinity, those slices become infinitely small, and the error becomes infinitely small. All right, let's see it in action. A pyramid 3 meters high, so it goes out to the 3 meter mark here. This picture is just a little bit hard to imagine, so I'm going to just put a little dotted lines in there to say, okay, so that's what we're talking about here. We're going out to a height of 3, so this pyramid's been put right along the x-axis. You can say, well, that's pretty convenient. Well, that's what we do. We put them right along axis to make it convenient. So whatever shape you have, you lay it right along the x-axis, and that works out nice. So a pyramid 3 meters high has congruent triangular sides and a square base. The square base sort of implies congruent sides, but this is like a regular pyramid, okay? And it has a square base, 3 by 3, and it says find the volume of the pyramid. So what we're going to do is we're going to say, okay, if we can do it, we want to go volume from A to B, from the lowest x value to the highest x value, and we want to find the area as a function of x all the way along the way, and we want to multiply it by the width of the individual slices we're going to do there. So in this particular case, what we get is, okay, let's talk about the limits first. We're starting at x value 0. We're going out to x value 3 way out here. So the limits are 0 to 3. We're going from height 0 all the way up to height 3. the area. Take a look at the picture. It's such a nice area. Every little slice you take out of this pyramid will be a square. So area of a square, x squared. Can it be that simple? Yeah, actually it is. Shockingly simple. And we're like one step away from being able to actually, for the first time since grade 9, prove the volume formula for pyramids and for cones, that 1/3, that mysterious 1/3, and for spheres, that mysterious 4/3. That's all going to come out of this. But for now, actual numbers, 0 and 3, instead of going from 0 to h, there's a little bit more work that has to be done before we can handle just any height. A general height. Here, we've given the height of 3, so we can work with that. The rest of it is pretty straightforward stuff. Antiderivative, 1/3 x cubed, evaluating between 3 and 0. So in the first bracket, 1/3 times 3 cubed. Second bracket, 1/3 times 0 cubed. And here I get, 3 cubes, 27. Times 1/3, I get a 9 in the first brackets, I get a 0 in the second one. So I get a 9 here. 9 what? We're talking about a volume, so we need cubed. We're talking about meters, so we're talking about meters cubed. So nice. The diagrams are tough to make. I won't lie to you. They give you the diagrams in some of the examples in the textbook. Other times you're going to have to make the diagrams yourself, and that's not going to be pretty straightforward. But hopefully these diagrams will help, looking back at them to help you through that. Okay, circular cross-section. Most questions can be handled like this when you're rotating any kind of, see this curve here, what they want you to do is take this curve and rotate it around the x-axis, which is tough to visualize. So they've done a beautiful visualization here of what happens when you wrap that thing around. And maybe the toughest part of this lesson is just to take 3 or 4 minutes and really stare at the shape that's on the top there, and really stare at the shape that's on the bottom and make sure it's clear to you what's happening is that curve is wrapping around the x-axis. It's being spun. Imagine we took the x-axis and actually spun it. What shape would we get in 3D? Well, it would map out this 3D shape you're seeing there. So what's nice about that when you wrap a shape around like that is you automatically get a cross-sectional circle every single time. It's even better. The function is the radius, the function value is the radius of the circle at each of these slices. So each of these like bread slices you're doing will come out to be a circle because of that symmetrical wraparound you're doing, and its radius will just be the y value of the function. So here we go. Here comes that nice formula again. Volume equals integral a to b, a at x dx. So that's the area of each of those little circles. And then the dx is the height. So really, when we go to do this volume, we're really talking about a infinitely thin little cylinder here. Yeah? So a little tiny cylinder in there. Go back to this diagram here to visualize it. We're making a whole bunch of these type of cylinders. Okay, and that's the area times its height. You know, that little dx here is the width of that little tiny cylinder you're building. Okay, from A to B. Well, they told us over the interval -2 to 2. So in this question, not much thought to put into those limits of integration. And then the area. Well, I do this in several steps for circular cross sections. I then go, okay, that's going to be pi times the radius squared. That's how I handle that. I like to be able to see that, okay, we're talking about circular cross sections, so it's going to be pi r squared every single time. And then what's the radius every time? Well, the radius is the function value every time. So then I get the function that they gave us, which was 2 plus x cos x. And I get that thing there, which is, that's a bear to do that integral. And you'll get later on to the point where maybe you got a chance at evaluating integrals like that. The good news is they said use a calculator here. So I'm going to use my calculator to punch this in. Just a review of that very quickly. On the Casio, I turn it on and I go to setup and I make sure I'm in math mode, not line mode. So I want to be in math mode there. So I went up to shift menu and then I pressed F1 to get it into math mode. Then when I do that, I get some stuff at the bottom, all these choices. You've got to arrow over. You got to hit F6 to arrow over to integral. And I hit integral and it wants the function first of all. So I'm going to hit pi. and then open a bracket, and I've got 2 plus x cos x. Close the bracket, square that bracket, and then arrow over, and then I can get to the lower limit, -2, get to the upper limit, +2, press enter. Ooh, came out pretty quick, so this isn't too complicated a numerical integral for it, and I get 52.43. It doesn't tell me what the units are for this one, so I just go units cubed because I'm talking about a volume. Okay, so straightforward. This one, the first one was a straightforward area. This one, when it's wrapped around like that, you're usually going to go right to circles. Now, the third big method is when something's being wrapped around but sort of has an upper and lower function. And this is the big challenge in this question. So they've got y equals cos x in the picture here. And they've only done a little bit of cos x. And they've done y equals sine x here as the lower function, and then taken that shape between cos x and sine x and wrapped it around the x-axis. And maybe that's what you have to do, is take about 5 minutes and take a look and see if you can see that that upper diagram, if you take that shape that you see in the upper diagram and wrap it around the x-axis, as if you're spinning the x-axis sort of on a rotisserie, that you get this shape in the bottom. And that's what they want you to do, is wrap this shape around to get that new three-dimensional shape. And we want to find the volume of that. Well, before we even start, we need to know what this x value is right there. We need to know, when does cos x equal sine x? And that, I'm telling you, that's going to come up. They love that in first year university, is throwing that at first year students and seeing if you know how to solve when cos x equals to sine x. Because factoring doesn't work, isolating doesn't work, none of that stuff works. You need some trig knowledge to be able to handle this situation. And the trig knowledge you need is that dividing both sides by cos x is a fantastic move here, because I get tan x equal to 1, and I know when tan x equals 1, I need 1 over 1, and so that's pi over 4. I don't have to do the cast rule or anything like that, because I'm just looking for the first quadrant solution, so I don't need to go any farther than that to find solutions. I only want that first one. So that tells me the limit I need for this integration. So here we go. Now, there's a problem with shapes like this where there's an upper and a lower, is that what you get is not a circular cross-section every time, and I hope you can see that on the picture there. You get this pink washer cross-section. It's just like a disc, like a record, if anybody knows what a record anymore. A CD, and it's got a little hole in the middle that's been carved out of it. So for those ones, we have a washer. And the nice thing about the washer is it's got a pretty easy formula. You take the area of the outer circle, subtract the area of the inner circle, usually used like this with the pi common factored out like that. So each of those cross sections has area pi, capital R squared minus little r squared. So same formula though. Volume equals integral from A to B of the area of that cross section times the little width of that cross section. And so in this case, I found out what the limits of integration should be, that we should be going from 0 to pi over 4. And the area, I like doing it this way. I go pi r squared minus r squared. I actually write that in there to remind myself I'm doing the washer method now, because the circles, it's not a full circular disc like it was here. It's not a circle cross-section like that. It's a washer this time. Okay, so now with the washer, I'm going to do two things at once here. I'm going to common factor that pi all the way out front. Much more convenient to deal with it out there. And then inside here, the big R is the upper function, this thing here, which was cos x. And the lower was the lower function, which was sine x. So on each of these things, I've got the radius of the big part, which was r, is cos x. The little r is sine x. So in each one, I got cos squared x minus sine squared x. Now this integral is a bear as well, and they love integrals like this in first year calculus because they love to know if you've got your trig identities down pat. And without a trig identity here, this this integral's a real bear. If you go to your trig toolbox, or if you look these up, and it'd be worth it to print out that trig toolbox for university, take it with you, and get used to what you're going to have to memorize. Ask your TA, ask your prof, which of these need to be memorized. We don't really make you memorize them too much in high school. But there's a beautiful identity here. Taking the integral of cos squared x is a real problem. And taking the integral of sine squared x is a real problem. But cos squared minus sine squared is cos of 2x. How nice is that? That's a much easier integral to handle and gives you a hint as to what all that identity stuff was about. It was about the ability to switch over to a easier form in these trig type questions. Now, the integral of cos 2x, that's a little more under control. That's half sine 2x from 0 to pi over 4. Still got that pi out front, so my first bracket is 1/2 sine. Okay, 2 times pi over 4 would be 2 pi over 4. That's pi over 2. That's the first bracket. And then, the second bracket is 1/2 sine 0 when I sub 0 in there. Let's see, first bracket, I get a sine of pi over 2 is 1. And so I get half of 1. So I get a 1/2. And then sine of 0 is 0, so that's a 0. And I'm all done. Pi over 2 units cubed. Folks, these methods need practice. They are not the toughest thing ever. I promise you they're not the toughest thing ever if you practice them out, because there's some methods coming up that are pretty tough. We need this down pat. We need these simple situations down pat if you're going to be able to handle the next couple of lessons that are coming up. Okay? So really, I know we preach this all the time, do all the homework, but it really is true today. You really got to attack this thing. You can't just watch this lesson and go, oh yeah, I get it, I got it. No, not good enough. You got to practice it and make sure that you've got all these little steps down pat for those 3 different types of questions. All right? So enjoy. One of the high points of the course in my mind is